Part 1 will look at a brief introduction to integrating spheres. We'll look at how sphere diameter can affect both transmittance and reflectance measurements. We'll look at some sample placement issues and how to measure specular samples in an integrating sphere. Part 2 will deal with applications. We'll first consider carbon nanotubes. We'll look at suspended nanoparticles and see a method for optimizing concentration, and also how we can use it for species identification. Lastly, we'll look at surface nanostructures, and for this, we're going to use butterfly wings as our sample. The first rule of integrating spheres is that in reality, all integrating sphere measurements should be considered approximately. Why? Because there have to be holes in the sphere to allow the light to enter, which also means light can escape through those holes. Therefore, you're not collecting all of the energy, therefore an approximate measurement. The first consideration is sphere size, or its diameter. The larger the sphere, the more internal bounces. The more internal bounces, the quote-unquote better the integration. However, the larger the sphere, the less energy will reach the detector because of the size of the sphere. The second issue is port fraction. Port fraction is that ratio of the total port area. Port area being anything that's not covered by the white reflective material. Holes, detectors, things like that. And it's a ratio relative to the total internal surface area of the sphere. The port fraction of a 150 millimeter sphere is about 3%, which is very good. A smaller 60 millimeter sphere has a port fraction of around anywhere from 9 to 11. Not nearly as good, but still very, very usable. A low port fraction also ensures a good integration, in other words, more bounces inside the sphere. Lastly, the coating material that's done internally inside the sphere. Unlike popular perception, the coating material does not have to be 100% reflective. No material is. The internal coating reflectivity influences energy or noise, not accuracy. So it doesn't matter if you have a barium sulfate sphere or a spectralon sphere, they will still have the same accuracy, but there will be differences in the noise. Typically, a coating reflectivity of 80% R or better is considered acceptable. Now, the very last part here. What does affect percent reflectance accuracy is the reflectivity of the target material for the background correction. In the world of integrating spheres, everything is a trade-off. And here we're going to look for a second at the difference between a barium sulfate sphere and a spectralon sphere and see their pluses and minuses. Barium sulfate spheres are much lower cost. Spectralon spheres are much higher because spectralon is a patented material and is exclusive to one particular vendor. Barium sulfate has a low reflection in the near infrared region because of water in the barium sulfate. Spectralon doesn't suffer from this. It still has a little bit of water as you go out into the near infrared, but it's a significant difference from barium sulfate. Both spheres can be used to generate absolute reflectance data if you use a calibrated target plate. With barium sulfate, it is easy to recoat a dirty sphere, and barium sulfate is not absorbent of dirt and organics, whereas spectralon is. It's a porous material. It readily absorbs volatiles and stains. And if you need to replace your sphere or resurface it, you really can't do that. You have to replace the spectralon itself. Now, for the next series of slides, we're going to be comparing both transmission and reflection data from a 60 millimeter sphere and a 150 millimeter sphere. First rule of thumb. If you really need to compare data between spheres, it is best to compare data between spheres of the same size. And you're going to see why. First, we're going to consider transmission. And transmission, as you can see by the little diagram at the bottom, can be either linear for a transparent sample. It can be diffuse, scattered for a hazy sample. And both of them together constitute total. So an integrating sphere in scatter T mode is collecting total transmission. And the first sample is a transparent linear sample. You can see that there is very little difference between the 60 and the 150 millimeter sphere for a transparent sample. A quick note here, as you may have noticed, the dye in these three samples of plastic is the same dye. They look different because of surface texture and dye concentration, but it's the same blue dye. Here we're looking at a sample that scatters a significant amount of light. It has a matte or a diffuse finish on it, and you can see there is a large difference between a 60 and a 150 millimeter sphere. Typically, the 60 millimeter sphere is always going to give you the higher measurement, and the difference is strictly the ability of these different size spheres to integrate. The red line is an average. So if you did need to compare a 150 to a 60, the best thing to do would be probably to average the two spectra together. Our final sample for transmission is a somewhat semi-opaque sample. You can see from the spectra that the amount of light coming through is drastically reduced. And interestingly enough, when you look at the spectra, there are places where they agree totally and others where they disagree. Welcome to the world of integrating spheres. This is very, very common. Both spectra are correct for the size sphere. Most people, however, would consider the 150 millimeter spectrum to be the better approximation of what the actual transparent percent T value is, and the 60 millimeter sphere data to be more of an approximation, but there is absolutely no way to predict areas where the two spheres will agree and the two spheres will disagree. We are now going to move on to reflectance measurements and a sphere comparison. And we have three different samples to look at. The first is a green opaque film. It is mostly diffuse reflectance with a small specular component. The middle one is a pink transparent specular film. Yes, I know it looks purple, says more about the color temperature of the flash in my cell phone than anything else, but it is pink. And it is mostly specular reflection with a small diffuse component. Lastly, we'll look at yellow spectralon. One of the interesting things about spectralon is it is a solid baked material, and you can literally bake pigments into the spectralon. And this is all diffuse. It has zero specular components. We will look at the two different measurements of diffuse-only reflection and total reflection, as you can see from the little diagram at the top. So let's first consider the yellow spectralon. As you can see, almost no difference between the total reflectance measurement and the diffuse-only. Between the 60 and the 150 sphere, there's roughly a 0.5% R difference. And this makes a very, very important point about integrating spheres. If you are measuring diffuse reflectance, which is what a sphere was designed to do, you will get almost no difference between a 60 and a 150 millimeter sphere. So to within, let's say, 1% R at worst. So this is very important to remember. If you're measuring a truly diffuse sample, then you can use either a 60 or 100 millimeter sphere and get the same number. The green opaque sample is a very good example of a sample that doesn't look like it has a specular component, but it does. And the reason why these two groups of spectra differ is because of the measurement type, not because of sphere size. You see that for diffuse only, the 150 and 60 agree closely. For the total reflectance, the 150 and 60 agree closely. But there is a difference between the diffuse-only measurement and the total reflectance measurement, which is a legitimate artifact of the fact that the sample does indeed have a small specular component. Our final sample, and our most problematic sample, is the pink transparent sample measured in reflectance mode on an integrating sphere. Rule number one in measuring transparent samples in reflectance mode on an integrating sphere: never put anything in back of the sample, especially anything reflective. It will cause a double pass through the sample and give you all sorts of weird and wacky data. Here, you'll notice again, the data correlates by the type of reflection measurement rather than the sphere size. You'll also notice that it's much lower because most of the light is passing through the sample out and is trapped out by the surround of the integrating sphere. So you're only getting what is reflecting off of the transparent sample here. And you'll see there's a significant specular component. The diffuse reflectance group is rather low, whereas the total reflectance group is higher because of the inclusion of the specular component. And there is a disagreement in the diffuse and the total group by sphere type, and that's simply because of the difference in integration of a sample like this. Let's talk a little bit about how samples fit up against the diffuse reflectance port of an integrating sphere. The size, shape, and nature of the sample can cause placement issues. All of these placement issues will yield a lower than expected %R result. They usually always give lower %Rs. The first one at the top is if you have a sphere. This is more of a problem with spectralon spheres sometimes than it is with barium sulfate spheres, because spectralon is a rather thick material that is milled, and you can have steep edges on the port if they're not chamfered, so that can basically trap out some light. The recessed sample is also a problem in that if your sample isn't right up against the port, it has a little tiny area that can trap out light. This is a problem with curved samples. So if you're using curved samples, place the convex surface against the sphere, not the concave surface. Lastly, if your sample is thick and hazy, you get, rather than the light simply going through the sample and out, it gets scattered around in the path length of the sample, and that light then gets trapped out, and some of it can get back into the sphere and cause an artifact. Our final sample consideration here is going to be about samples that have a texture to them. This is most predominant in fabrics that have a weave that has a certain orientation. You can see here in the example we have a fabric with a distinct weave placed in 4 different positions, and you can see that it gives 4 distinctly different spectra at the top. And there's literally nothing that can be done about this because the fabric is literally acting as an organized series of light traps, and how you position those light traps will literally give a different intensity spectra. The qualitative nature of the spectra is the same in terms of the peaks, but the intensity is different. The only solution is to present multiple orientations to the beam, run multiple spectra, and average them. Let's take a second here to drop back and consider how a sphere looks at diffuse and specular samples. On the left, you see the reflections of what happens off a totally diffuse sample. You can see light comes off at all angles and is then multiply integrated or reflected off of multiple bounces in the sphere. A specular sample on the right causes the specular component strikes a given area inside the sphere, and then it reflects off of that. But what happens with a specular sample is it generates what's called a hot spot in the sphere, and that can cause some issues. Now, depending on your sphere design, some spheres direct the specular component into the sphere. Others direct the specular component out the entrance port, and how you deal with those samples may well depend on the sphere design. Here's a look inside a sphere with my nifty new fiber optic camera that I was able to use. At the top, you see a diffuse sample. Notice how the light is evenly distributed around the surface of the sphere. The sphere surface just looks bright. This is what's supposed to happen. This is the integrating sphere integrating. It's making a smooth illumination of the inside of the sphere. Down at the bottom is what happens when you have a specular component. You can see the hot spot. Even from only a 10% specular sample, a significant hot spot is generated. With a 90% sample, it is much brighter. Notice how the rest of the sphere is very dark. This presents a significant problem if you are trying to measure a specular sample, a truly specular sample in an integrating sphere. Not that you can't do it, but you just have to be aware of how to handle a specular sample in a sphere. So this is the comedy of errors that occurs when you attempt to measure a specular sample and you have used a white diffuse plate, be it barium sulfate or spectralon, as the target plate for the background correction, and you now have a hot spot by these samples in the sphere. As you can see, we have a NIST mirror, we have a polished aluminum mirror, and we also have a silica plate. The silica plate is a totally specular surface, but it appears dull. Not hazy, it just appears dull because it's not as reflective as aluminum. As you can see, numbers above 100% are totally artifactual. So when you've background corrected with this type of diffuse plate and run a specular sample, your photometric values are in error. It distorts the spectral features. Your peaks kind of move around and get fat or skinny or whatever. And you also have these nasty changes, these steps at the detector grading change if you've got a UV visible near-infrared instrument. The way to solve this is to background correct on a calibrated mirror. What you're doing is you're attempting to duplicate the hot spot inside your sphere with your background correction and therefore cancel it out. It's not the most perfect way to do it. But it will work, and many people have used this. The better your mirror that you're using for your background correction is like your sample, the better your data is going to be. So for our final slide in part one, we've picked the topic that only true sphere aficionados will have any knowledge of. And that's the fact that a sphere is incapable of producing a zero. Even if you put the blackest material on the face of the earth up against it, it would not read zero. And the reason is because the beams of the spectrophotometer must go through the sphere before they strike the sample. And that means there's a very small amount of light scattering within the sphere that you literally cannot get rid of, but you can measure it and correct it out. I've shown you three things here that people tend to use for this process. One is black spectralon. This is literally spectralon baked with carbon black in it, and you can see it's not really black, and it changes as a function of wavelength. Some people use an open port, and with that we get closer to what the true zero probably is. This is just opening up the port, let the light go out, and only measure the scatter in the sphere, but a little bit of light gets back in. The best way to do it is with a light trap. This is a device that has depth to it and fibrous material painted black. A light trap probably gives you the best approximation of what zero is for that sphere. It's usually going to be a number lower than 1% R, typically between 0.3 and 0.5% for most spheres.
Thank you, Dr. Taylor, for the part one of the presentation. That was a lot of exciting stuff. Now we'll answer a few questions we've received so far. All right, let me look at the first question. Here it is. It looks like sphere size is more a factor for transmission data than for reflection data. Is this typical?
Yes, it is. You have to remember an integrating sphere was designed for diffuse reflectance. It can also do scatter transmission, but the optics are a little bit different in terms of the sphere. When you're looking at scatter transmission, the light is spreading out from the sample that's placed in the scatter transmission port, and you have the possibility of more of a direct interaction with the detector before the light bounces around inside the sphere. And this would, of course, be a slightly more of an issue for a smaller sphere than a larger sphere. So you will see more variation in scatter transmission measurements.
All right, thank you. The second question, we do have time for a few questions, so we'll go with the second question. Why would you want to measure specular samples with a sphere rather than a dedicated specular reflectance accessory?
This is actually an excellent question. Normally, one would use a dedicated specular accessory because that's what that accessory is designed for. And I mentioned that you can make hotspots in a sphere with the specular sample. But there are industries that must measure the total reflection off of a specular sample. A good example is the solar industry, where you're looking at specularly reflective surfaces that have texture to them, and they need to measure the reflectance of everything, both diffuse and specular. So from that standpoint, they're measuring predominantly a specular sample, but they need to also measure the total reflection and the diffuse as well, all as one measurement. So it really depends on the industry and the requirements as to whether or not you would want to measure a specular sample on a sphere.
Thank you. Just to follow up, and a question from me to you. So it is safe to say that having an integrating sphere will give you the ability to do both specular and diffuse reflectance, while the specular reflectance only accessory will do only one type of measurement. Is that correct?
That's correct. Specular reflectance accessories are designed exclusively to measure specular reflection. They will not measure any diffuse component, but they will give you the best possible answer for a specular sample.
Right. Thank you. Another question, and this is a very interesting one, and this applies to, users and how to mount the sample. So here it is. How do you put gels and creams in a sphere to measure them?
You would mount them on a transparent substrate, typically a quartz plate. Now, if you just take a smooth quartz slide and you try to put a cream or a gel on it, you're going to be somewhat disappointed because you're not going to be able to get a nice homogeneous distribution onto a smooth surface. They do make quartz plates that are designed to put creams and gels on, and they are centered. They have a structure to them that has pockets that allows the cream to go into the pockets. So it's very easy to smear your cream onto this, take a straight edge like a popsicle stick or something like that and take it over the surface, and you can actually reproduce path length on that because the pockets will be of a certain depth, and if you clean off all the sample above the pockets, this is widely done in the sunscreen industry where they're doing scatter transmission measurements of sunscreens to get SPF values, and they use these centered quartz plates that have these pockets that allow the gel or the cream to fit nicely into.
Great, thank you. That was very helpful. Well, let us now proceed to the second part of the presentation, and we'll answer any remaining question at the end of the presentation. Here you go, Mr. Taylor.
The first application we're going to consider in Part 2 regards single-walled carbon nanotubes, or SWCNT, and it's a network of sp2 hybridized carbon atoms. Actually, it's a sheet of graphene that you react it rolls up and connects to itself, and it forms these sp2 hybridized regions where any individual carbon in them, depending on its orientation and placement, can be either metallic or a semiconductor, and we'll look into this in the next slide. So here are two schematics showing you the band gap energy structure, as an electron progresses from the ground state up to the excited state with the absorption of light energy. The one on the right is for the metallic transition, and you can see that has a rather large energy indicated by the arrow. The semiconducting band gaps, on the other hand, are, you can see, much smaller, and there are two of them. One about medium and the other one smaller. What this means in the world of UV visible spectroscopy is these electron promotions are associated with the absorbance of energy. The larger the energy, the shorter the wavelength. So the metallic will be at short wavelengths, whereas the semiconducting smaller energy transitions will be in the long visible and near infrared. So let's bring this down in a way that we can see what UV visible near infrared spectroscopy can do for single-walled carbon nanotubes. Here we see a spectrum of a typical nanotube. You can see that it has peaks in the metallic region, which would be from 300 to about 500. The first semiconductor region is from about 500 to 900. And the third semiconductor region is actually in the near infrared, going up to 1400 nanometers. Spectroscopy of single-walled carbon nanotubes can be used to identify chemical species. It can be used for purity analysis. It can be used for quality control, research and development. You can see here that the peaks are rather numerous, and you can use these peaks to identify different types of single-walled carbon nanotubes and their purity. A very brief commercial announcement. Shimadzu has an instrument called the UV2600 that can be purchased with an integrating sphere with an in-gas detector that is perfect for this range because it goes all the way up to 1400 nanometers and all the way down into the UV. It is small and relatively inexpensive for a UV visible near infrared instrument, and again is perfect for this type of analysis where you need the lower part of the near infrared region. So we'll now turn from carbon nanotubes to other types of nanomaterials which can be used in either a suspension, they can be used in creams such as sunscreens, and they can actually be impregnated into surfaces such as clothing where they might form an odor-reducing component. So UV visible near-infrared spectroscopy is a very useful tool in analyzing nanomaterials no matter where they're embedded, be it solid, cream, solution. The first question to ask is, what concentration is amenable to analysis? Here we see, other than being a picture of my thumb and forefinger, you see a cuvette holding 4 different concentrations of silicon dioxide nanoparticles, or sand. And you can see we've gone from, on the left, oh my gosh, is that too much, to all the way on the right, which is, gosh, is there anything there? So I'm going to outline a little methodology that can allow you to determine the best concentration of your nanoparticles in solution. So you may notice as we go through part 2 here dealing with applications, all of these applications are performed on an integrating sphere, which was the reason for part 1 of this webcast. Here you see spectra of the 4 different solutions we saw in the previous slide. And you can tell a little bit by eyeballing here. You can see maybe that the most concentrated one at over 200,000 parts per million might be too much. What's clear is that we seem to be suppressing the peak structure below 350 nanometers as we go to higher concentrations, but are we suppressing out useful information? So just by looking at the scatter transmission spectra may show us when we have too much, but it doesn't necessarily allow us to pinpoint the nanoparticle suspension that might be optimal for analysis. So the method we're going to adopt here to look at which concentration is the best is a modification of the Hayes measurement. Now the Hayes measurement consists of 4 measurements. 2 of them are background correction or zeroing measurements, which are T1 and T3 here. and the other two are identical measurements with the sample in place. And if you look at what's going on, you'll see that what we're doing here is that we're removing the diffuse reflectance target plate. When the target plate is in, you're measuring all of the light that comes in, scattered and linear. With the T4 measurement, with the plate out, you allow the linear transmitted light to escape the sphere, and you measure only scattered in the sphere. So when you ratio the T4 to the T2, this is what we're going to call the scattering capacity. We're going to simplify this to just two measurements because we don't need to be terribly quantitative about this, so we don't need the two blank measurements. So we're going to use T4 and T2 as the scattering capacity, and this is basically a ratio of the diffuse scattered light to the total transmitted light. And as you can see here, if you have a sample that's totally transparent and doesn't scatter, you're going to be reading 0. If you have a sample that's fairly opaque and totally scattering, you're going to read 100%. Here you see a plot of the scattering capacity on the y-axis as a function of wavelengths. And you can see that the scattering capacity is much more sensitive to showing you what is off scale than a simple scatter transmission measurement. You can clearly see here that the higher concentrations are flatlined up around 100, or essentially they're going off scale. You can see that the 2,000 part per million just barely squeaks in as we get to 200, but really the 200 part per million would be optimal because all of the scattered light is within the measuring capacity of the instrument. Now, the reason for the shape here being increasing as it goes to shorter wavelengths is because Rayleigh-Tyndall scatter, the small particle scattering, the intensity is a function of wavelength, with short wavelength light being scattered much more intensely than long wavelength light. And that's really the reason why the fog buster headlights that you have on your car are red. The red light, or the longer wavelength light, is not scattered by the fog nearly as much as the blue or mid-visible light would be. Now that we've found the optimal concentration for nanoparticles in solution, we can now use it as a tool to possibly tell the chemical nature or the species of the particular nanoparticle, particularly if the nanoparticles are metal or metallic oxides. Here you see 3 scatter transmission spectra of silicon dioxide and 2 metal oxides. The silicon dioxide is rather unexciting, but the 2 metal oxides do show some peak fingerprinting down in the UV region that could be used to determine what type of composition the nanoparticle has. Now, the next step to possibly bring out more definitive information would be to do an absorbance transformation on the scatter percent T measurement. And as you can see here, the absorbance transformation does very little for the silicon dioxide, but for the 2 metallic oxides, you can see it heightens the peak and gives you a little bit better separation and more definition. We can go one step more than this and do a second derivative of these absorbance spectra to maybe even get better information. So here is a second derivative transformation of the absorbance spectra you were just looking at. Now, for those of you that are not familiar with what happens in a second derivative, every place that there is an absorbance peak, you would get a downward inflecting peak in a second derivative, or a minima. So if we're looking for peaks here, we should be looking for minima. So if we see the silicon dioxide, kind of noisy, not a lot of definition, but there looks like there are some peaks at around 300 and around 250 or 260 that could be used for identification. The metal oxides are far more defined, with 3 distinct peaks and very little noise. So even if we had a mixture of these 2 metal oxides in suspension, we could probably identify them because their peaks here in the second derivative are fairly well separated. So you can see the utility of a second derivative transformation. So let's revisit the scattering capacity spectra for just a second. Here you see the scattering capacity spectra of the two metal oxides and the silicon dioxide from the previous work. You see that only metal oxide 2 gives a peak or structure in the scattering capacity spectrum. So it certainly won't work with everything, and it would be very difficult to try and estimate what species of nanoparticles might give a signal, but it's certainly a tool to keep in your toolbox to investigate if you're having trouble getting separation or identification on a particular nanoparticle species. So now we get to the important stuff. Most industrial applications of nanoparticles do not have nanoparticles floating around in solution unless you're doing wastewater analysis or pollution analysis or something like that. Most industries are placing nanoparticles into products, be it fabrics, paper, creams. The nanoparticles are in some sort of product. So can we detect the nanoparticles in something other than a solution? So to simulate this, we put nanoparticles on a piece of filter paper, and the first question is, can it be quantitative? Here you see 3 different concentrations, and you can see there is a distinct difference in the scatter transmission spectra. We're shooting the light through the filter paper. You can see that there is a semi-quantitative correlation between amount of nanoparticles and the spectra. So let's follow the procedure that we just described. We'll take the scatter transmission spectra of our nanoparticles on filter paper and take those 3 species of nanoparticles, generate their scatter transmission spectra, convert them to absorbance, and take a second derivative. And lo and behold, you can see the second derivative spectra of the 2 metal oxides and the silicon dioxide very closely resemble their solution counterparts. Now, it is not unusual to have some shifting and broadening of peaks and so forth as you move from a liquid environment into a solid environment. So you would expect some subtle changes, but the definition in being able to identify these species on a piece of filter paper is absolutely huge in terms of industrial applications. So, the take-home message about nanoparticles and UV visible near-infrared spectroscopy. You can use both transmission and diffuse reflectance mode of an integrating sphere to investigate nanoparticles. More importantly, a wide variety of substrates can be measured. Fabrics, paper, glasses, plastics, liquids, gels, creams, even human skin. You get the idea. If you can mount it against a sample port, you can make a measurement. So it's not unfair to say that every single nanoparticle lab that is doing either R&D or quality control should have a UV visible or UV visible near-infrared instrument with an integrating sphere. So let me finish up this webcast with a topic that I hope you'll find both interesting and fun. One of the more innovative areas of nanoparticle research is putting things like transparent metal oxides onto substrates. It's used in the solar industry to try and bend and focus light on solar cells, but there's a lot of people looking to put nanostructures and adhere it to a surface rather than just impregnating it. So insects almost exclusively produce their color by physical diffraction, not necessarily by pigments or dyes. And this is because they have a hard exoskeleton of chitin, and you can produce very small structures in this that can literally diffract the light. So here you see a picture of a butterfly wing. Let me be very clear. No butterflies were harmed in this study. My wife put this thing called a butterfly bush out in back of my house, and it performs as advertised. Literally attracts hundreds of butterflies. Some of them undergo and have a natural death and fall to the ground, and I pick them up and I have used them. So no butterflies were sacrificed or injured to get wings for this study. But one of the things that you'll see here in this photomicrograph of a butterfly wing scale is we have very small, tiny structures on this wing that are responsible for producing colorations. And I would like to take you on a little investigation of these structures. We're going to start out by looking at this particular butterfly wing that has white spots, it has black spots, and it has orange spots. And we're going to start out looking at the white and the black spots. Here you see a reflectance spectra of the UV visible near infrared of a white versus a black spot. You can see they look very similar in the near infrared, and it looks like there might be some differences below 1,000. So let's look a little closer. The white and black spots on the wing are areas that are not diffracting, they are simply reflecting light differently. You see in the photograph at the bottom these rigid structures and these small holes in it. The white spot has the bottom of that cell closed up where it reflects back, whereas a black spot, it's open and the light passes through. Now, what's important to realize here is the wavelength of light that's reflecting carries information about structures that are similar to the wavelength of light. So the near infrared would be looking at larger structures than the UV and the visible. I've normalized the spectra here to, so you can see that there's really no qualitative difference in the near infrared, and that's because you're basically looking at those large support structures there that are white. When you get to below 14 or 1300 nanometers, there is an intensity difference that is because of the amount of light reflected from the opened and closed holes. Here we see a second derivative of the near infrared region, and you can see there's zero difference between the white spot and the black spot. And the reason for this is because that there is no difference in the support structures that are fairly large here are the same between those two spots, and there's no difference in the spectra. Now, one thing it's worth mentioning here, when you're dealing with reflectance spectroscopy, you never want to use that you've made an absorbance calculation or you've done an absorbance conversion. When dealing with reflectance, you would do the log of 1 over R, which is the absorbance analog for reflectance, and then this second derivative was done on the log of 1 over R transformation. It's just a matter of correctness in not using the word absorbance when dealing with a reflectance measurement. So here is the same second derivative of the log of 1 over R for the UV visible region. And you can see that there is a difference, but it's mainly an intensity difference. Most of the peaks here and the troughs do line up, indicating we're dealing with the same qualitative spectra, but what we're dealing with is basically an increase in the reflected light back because the white spots have the bottom closed up and are reflecting more light, and this is supported by the fact that there are very few, if any, qualitative differences here. So now let's move on to the orange spots, and you can see from the pictures here that the coloration appears different between the front of the wing and the back of the wing. The back of the wing is what has the black and white spots. The front of the wing doesn't have any, it has black areas but no white areas. But the orange areas are shared in common between the front and the back, but they look very different in terms of intensity. If we look at the spectra here, we see that we have an isoreflective point there at around 800 nanometers, where the front and the back of the wing are equally reflective, and then the back side becomes slightly higher than the front side. So let's take a look at this with an absorbance equivalent transform. So here is the log 1 over R conversion for the front and the back of the wing, which is the absorbance equivalent in reflectance. And you can see that indeed, starting at the visual sensitivity of the human eye, around 750 to 800, there is a distinct difference between the front and the back that accounts for the front being a little bit brighter and the back being a little bit duller. And this does indeed stand out in this particular plot. So is this orange color due to the absorbance due to a pigment or from nanostructure scatter? What I've done here is I've put it in a gray area that shows the sensitivity of the human eye, and you can see that you can't see a whole lot from the parent spectra of just the percent transmission or log of 1/r, but when you do a second derivative, you now see distinct structure of at least 4 peaks within this region from 800 down to 500, which is exactly what you'd expect for an orange or a reddish color. Now, the original percent R looks like it could be the cutoff of a simple pigment. Most pigments function by simply cutting off at a certain wavelength. However, there is a hint of some peak structure within that would not be necessarily due to a pigment. So the second derivative kind of pulls this out and shows us that there are 4 distinct peak structures there. So finally, let's see if we can confirm this by looking at a couple of pictures. On the left, you see a photomicrograph showing you the larger scales of the butterfly wing. And then on the right, we zoom in. We can see once more our support structures running horizontally there. And if you look closely down below them, you can see vertical support structures that are much smaller. And within that are tiny little ellipsoidal nanoparticles. And if you note their structure and their size, they are ellipsoidal, they're not round, and they're around 500 to 800 nanometers in size. This is exactly where you'd expect the size and shape distribution to be if this orange coloration is caused by diffraction. And indeed, it looks like, looking at the photomicrographs, that these small structures are responsible for the orange coloration by diffracting the light. And you can finally see that we could easily see this in the previous spectrum. On the last slide, it shows those 4 peak structures that are caused by these ellipsoidal nanostructures. So this brings our webcast to a close. I hope everyone found it informative. I thank everybody for their time and their willingness to participate, and we'll now have a few more questions that we'll answer to finish up the webcast.
Thank you very much for such an exciting presentation, Dr. Taylor. We'll now answer some of the questions that were received. The first question I have is, how is there chemical information contained in the scattered light from suspended particles?
That's actually a really good question. In the world of spectroscopy, your interaction with the sample is all about path length. In a typical UV instrument, you've got a quartz cuvette, and you know the path length because it's the size of the cuvette. When you move to a diffuse reflectance measurement, you're still making a measurement that contains path length, but it's just a much smaller path length. So if you happen to take, say, a film sample, a plastic film sample, and did a transmission measurement, and then turned around and do a diffuse reflectance measurements, the spectra, as we saw in the earlier part of this webcast, are still the same because it's the same chemical information, but their intensity or their absorbance or their reflection will be different because the path length is different. So for a diffuse reflectance measurement of a solid, the path length is usually much smaller, but it's still carrying the same absorbance information as what you got from a liquid in a transmission measurement. For particles in solution, you're dealing with the same type of measurement as a diffuse reflectance measurement, except these particles are now suspended in a solution rather than on a solid at the diffuse reflectance port. But the information that's carried is still the same. The only difference is when you're looking at suspended particles, you're going to have interference from light scattering that's happening, which can be wavelength dependent if the particles are small, and you're also dealing with the same small path length, but the chemical information in those small suspended particles is the same.
Great, thank you. The next question I see here is about butterfly wings. All right, this will be exciting. How did you physically mount the butterfly wings for the sphere?
This is going to be horribly anticlimactic. You take the butterfly wing and you get double-sided tape from any art store that has tape that has sticky on both sides, and you get a nice black piece of construction paper. You put the butterfly wing on the construction paper and tape it there. That gives you, depending on the size of the butterfly wing, it gives you a solid support in back of the wing and something larger to grab a hold of to put up against the integrating sphere. What you will probably need to do is most integrating spheres have large beams, and that's intentional. If you're trying to hit a certain spot on a diffuse reflectance sample, you may need to aperture the beam. This means you might want to get, say, an iris diaphragm and aperture the beam before it goes into the sphere. Or sometimes, and you have to be careful with this, you can focus the beam with lenses. But you must be careful to get lenses that do not have chromatic aberration. You don't want your lens to be bending one wavelength of light more than the other, but they do make lenses with coatings that do not contain any chromatic aberration. Using a lens to focus to a small spot is probably the best solution because it does not attenuate the energy of the instrument. You manage to get all the instrument down onto whatever spot size you want. You can get different strengths, different diopter lenses that will focus across different distances. So that's really the only sticking point of running any smaller sample on an integrating sphere is you may have to aperture and focus the beam.
Thank you. And just to follow up on that, while Shimadzu does include standard holders for films, powders, and nice and flat samples, any atypical sample like a butterfly wings, we do provide help and consulting in a way to help you mount the sample properly and to get a desired good result. With this, looks like we're nearing the end of our allocated time for the webinar. Thank you all for the interesting questions. In fact, there are a few that we were not able to get today, so we'll reach out individually to each of you whose questions we are not able to answer. Once again, thank you all for attending and participating. We'll send you an email with a link to view a recorded version of this presentation whenever at your convenient time. We hope to have you back in webinars we organize in the future. Have a great day. Thank you.